¿Se escucha bien? Okay, good evening, everybody. Thanks for coming. I'm going to show a recent development that I have been carrying on around this subject of allosteric communication, and I did change a little bit the title, and now the title is Allosteric Communication and Heat Diffusion in Protein Structure. I work with Carlos González and Ramón Latorre from CINB, Centro de Neurociencia Valparaíso, with Fernando González en el Centro de Bioinformática y Biología Integrativa de la Universidad Andrés Bello, y soy ex miembro de, o todavía estoy miembro del grupo de nanomateriales del Departamento de Física de la Universidad de Chile. Bueno, so allosteric communication is a central and not yet solved problem in structural biochemistry that determines the process of signal transmission through the three-dimensional structure of single proteins from short to long scales. This phenomena mediates the process of modulation of cellular proliferation, cellular metabolism, genetic expression, and enzyme activity. So it's key in the development of normal physiological functions and is determinant in some human diseases. Also, well, the word allosterics come from the Greek allos, that means other, and steric means space. So the regulation of an active site in a protein occurs in other side of it. Despite the advances on biochemistry and molecular biology, the structural and the energetic underpinnings that mediate the signal transduction in proteins is still poorly understood. So this problem, for me, constitutes a molecular scale biological challenge that I have decided to carry on. This is the outline of the presentation. I will start with some structural definition of protein structure and example of allosterism. Then I will talk a little bit about a very small protein that transfers signals in biology and about heat diffusion in alpha helices. Then I will take a look of thermosensing in living beings with sensors that measure heat in the skin, and some working hypotheses, and then conclusion and acknowledgement. Well, proteins are constituted by building blocks called amino acids. Maybe all of you are familiar with it. Here we have 20 of them. There are 21 or more, but we have here 20, and the difference between these building blocks is the chemistry that they carry on. So we have a set of non-polar amino acids, polar, where you can see, you can imagine a dipole or a multipole here in these groups, and amino acids that are charged in physiological pH, in water solution. Negatively charged and positively charged. I think the battery of this is not working. So proteins are formed by condensing one by one of these amino acids. So you have a dehydration when you bind any of these two, and you can have a linear structure, which is called primary structure, where you can have go on condensing, and you can have until n amino acid to form a primary structure. Here is a cartoon of the primary structure where each bit represents one amino acid or residue, which is what remains after the condensation. There are 4 levels of organization in proteins. This primary structure can form helices, or can form so-called beta sheets that are a kind of spaghetti that is connected by loops that are not shown here. Then this secondary structure can condense or be compacted upon themselves and form what is called a tertiary structure, which is an already active biological unit, a protein or an enzyme that can be further form higher order complexes by dimerize or tetramerize that can also have biological activity. So you see here, let's say we have beta sheet structure connected by loops and alpha helix connected by loops to the rest of the protein. Also, these two kind of structures are stabilized by hydrogen bonds. This is one protein, a small protein that is called PDC2 that acts as a signal transducer in living beings, and several in virus, also in fungi and bacteria. That has 96 amino acids and 1,1500 around atoms. So you can see the complexity of the problem here. What I'm trying to understand is how this network of atoms transfer signal from side to side. Particularly this protein transfers signal from this side to the other side. As another example that I'm working with, which is more complex, is an ion channel that have 2,500 residues, almost 40,000 atoms, which is more complicated. But they operate allosterically under the same principles. So it's recommended, I decided to start with a small protein, which is this PDC2 protein, in order to get familiar with the phenomena. And then I decided to scale the problem. You can see there are many atoms, so the problem became more and more complex. But the same principles are below. So let's see a little bit of examples of cellular and metabolic regulation by allosteric. One example may be the glucose uptake by cells that is mediated by an insulin-triggered response. Here you have the outside of the cell where you can find glucose, the plasma membrane, and the inside of the cell. And when insulin, this small molecule, bind this receptor, activate or transfer a signal throughout the structure to the inner side of the cell that triggers another responses that facilitate the transport of glucose to the inside. And the problem that I'm trying to study is located here. Here I'm studying the response of the receptor from the stimuli, or the chemical stimuli. Another example, let's continue with glucose, is the degradation of this molecule for energy production. This is a metabolic pathway, the degradative pathway, that is highly regulated. I will show one example here. Inside of the cell, glucose is phosphorylated by a protein, an enzyme which is exokinase, and a phosphate group is installed in the this is a 6 atom molecule. So the phosphates fall in the carbon atom number 6 by a reaction that it consists into the hydrolysis of ATP that form ADP and liberate this phosphate that is installed upon the molecule. Then this molecule suffer a small conformational change that so it's received the number the name of fructosa 6-phosphate that to which that suffered another chemical modification by this enzyme PFK, phosphofructokinase, that trigger that facilitate the same transformation. So another phosphate is incorporated to this molecule. After several steps, too much steps, ATP is restored. So many molecules of ATP are synthesized. There are a net gain. And the interesting part here is that the same ATP exert a negative feedback upon this enzyme or a negative allosteric regulation. And at this scale also, I am interested in the study of this problem. And the pathway became blocked. So here we have a cartoon of PFK, phosphofructokinase, that shows two sites. One active site here that binds fructosa and ATP. In yellow, you see the phosphate. This phosphate is going to be transferred to fructose to form fructose 1,6-biphosphate, and a secondary site, regulatory site, that bind ATP. So the problem here is which is the nature of the signal that travels from here to here that makes that make the negative feedback upon the system. So that is the problem that I'm trying to study. Fortunately, the thermodynamics of the allosteric communication is it's well defined. The free energy of allosteric signal is partitioned into an enthalpic and entropic terms, and the enthalpic part has been related to a three-dimensional change in the protein, and the entropic part of the phenomena had been related to a change in the vibrational dynamics of the protein. So, in this example, this previous example, the enthalpic part will make, let's say, that separate this site by a conformational change, and the entropic part that it is a change in the vibrational dynamics of the protein around the same three-dimensional conformation will help to modulate this system. So there are three types of allosteric. Type 1 with subtle conformational change that is entropically driven, in which the enthalpic part is almost zero. Type 2 driven by entropic and enthalpic components in different extent. And type 3 that it's driven by enthalpy. So the type 1 is the most mysterious one. And I think that this is the central problem on this phenomenology of allosteric communication. Type 2 and 3 have been long been studied, so there is a lot of information about these two types of allosteric, but this is the central problem. I consider that it's the central problem. So just to make a review, allosteric regulation by conformational change. When there is an allosteric inhibition, we have an enzyme that have an allosteric site that, when the allosteric inhibitor is binded, produce a change in another side of the protein that impedes that a substrate to enter here. A positive or allosteric activation reshape the active site so the substrate can bind. In order to have an idea of what a conformational change it is, this is a conformational change, a huge conformational change, several Armstrong change. This is a kind of Pac-Man, it's exokinase. When it's bind glucose, it changes a lot. And allosteric regulation without conformational chain was proposed in the 80s by Alan Cooper. You can review this. It's a very interesting work written in terms of statistical thermodynamics. And the phenomenology is here. We have a protein that have two sides, and when the effector binds on one side, facilitate the binding of the substrate, but without conformational chain. Without this effector, this pathway cannot occur. And the overall phenomenology responds to an increase of vibrational vibrational entropy of the molecule of the protein around the same structural average conformation. Well, this is the problem. We have many atoms. We have an entropic-driven and allosteric modality that I am interested on it. Some years ago, 10 years ago, this researcher proposed that the intramolecular signal can be correlated with the heat flow pathway in a protein. So I decided the idea is that the allosteric pathway follows the topology, the internal topology of the protein. It can be known experimentally which residues are part of the allosteric pathway. And there was an idea that if we hit here, the heat diffusion is going to be developed throughout the allosteric pathway. So I decided to study this idea, and a paper that I did publish this year, and in this journal show that this is the case, more or less. And for this, I did study this small protein, which is the PDC2, that have an allosteric role without conformational change. Here we have two cartoons of the protein and the ligand. So when the ligand binds the protein, there is no significant change in the crystal structure. The loops change a little bit of the termini change, but the core of the protein still remains with its three-dimensional structure. So I did use a computational technique that is called anisotropic thermal diffusion, that consists in to cool the model and to heat up one of the residues and relax the system after a given time, and then study how the vibrational energy is distributed in the structure. Interestingly, in this kind of system, in protein, heat does not flows radially, but it flows anisotropically, in an isotropical way. That means that follow preferential pathways, and this pathway of heat diffusion are the allosteric pathways. So what I get finally, after all the measurement, is a thermal map. So in this thermal map, I have an axis which I call it the pump axis of the heated residue axis, and a responding axis. So this is the protein, and if you review the paper, you will see that more details. But in general, it was known that there are two pathways, allosteric pathways in this protein. One pathway that runs from beta sheet structure 2 to 3, 4, 6, and 1, and from beta 2 to alpha 1. So if we look at the thermal map, when a pump is exerted in beta 2, I get a clear signal around here that corresponds to beta 3, beta 2 to beta 3. If the pump is done in beta 3, I get a signal around beta 4, beta 3, beta 4, and then beta 4, I get a pump, I pump in beta 4 and I get a response in beta 6, and beta 6 transfer energy to beta 1. So the information of allosteric flow is recovered. This was known previously by other students, and this study did confirm that the heat diffusion pathways are the allosteric pathways. For the case of the ligand, it's not shown here, but it's the response of the thermal map is shown here. The pump in beta 2 generate a response in alpha 1, beta 2 to alpha 1. So there are, at least I can recover the allosteric pathways with this technique. There are more couplings, and that may be another auxiliary pathways for heat diffusion and signal transfer. One interesting thing that come out of this study, that these are a result of 20 different measurements. So there is no asymmetry. Let's say the response in beta 1 when I pump in beta 6 is not the same when I pump in beta 1 and measure in beta 6. So it's not symmetrical. And this was very intriguing for me. And I decided to study in detail, and I did discover that here we have a detail of, in this part is, I cut here, so I get this zoom here, and this part is the zoom of this lower part. So I find that there is one, maybe the reason could be the anisotropical structure. For these two, if you see, they are asymmetrical, and I did choose one in the thermal map. Each pixel represents the coupling of sites. So here is 5 coupled to 91, 5 residue 5 coupled to 91, and the response is soft. But if you invert the heating and you heat in 91, the response in 5 is increased. So there is an asymmetry of energy flow. And when I went to the structure, I did find that it was an hydrogen bond that was mediating the interaction between these two amino acids, that leads to propose that the heat diffusion is favored in this direction, but is not symmetrical in the reverse direction. And the intrinsic asymmetry may be the origin of this effect. And it's proposed that it can act as a thermal diode or a thermal rectificator. If we look to another part of the same zoom that I have here in the screen, we see, let's say, this part is very symmetrical with this part. That represents the interaction of these 3 residues. And the difference with the previous case is that there is a short hydrogen bond, is shorter than the previous case, and the response is symmetrical. Let's see, 86 with 10. If we pump in 10, we have this response in 86. And if we pump in 86, we have the similar response instead. So this effect of thermal rectification, it seems to be modulated by the length of hydrogen bonds. Another source of asymmetry flow in proteins did arise from this observation that here we have a loop that is in interaction with a single residue. This is the loop. You can see the loop here interacting with this residue, and the response in the map is this. So when I pump in the loop from 13 to 17, from 13 to 17, I get a strong response in 43. But when I pump, when the pump is done in 43, I only get a response in 50. So the origin of thermal rectification, or the origin of the signal asymmetry signal diffusion, it's obey to the topological structure of the protein, in which it has a kind of funnel-like structure. It was previously similar structure was have been reported in carbon nanotubes, in which the similar cone or funnel-like structure are reported, in which the heat flow easily in this direction, but with difficulty in the reverse direction. Also, this kind of two nanotube of different diameters show the same property. And trapezium and this kind of structure also. So the importance of this finding is that this effect of thermal rectification may be useful to develop thermal memories and thermal transistor that may be useful in molecular computing or the design of digital devices based on heat instead of electrons. This is a secondary paper that appeared this year also with Gonzalo Gutierrez and me, myself, and where we show that the similar effect is observed in alpha helices. In these are helical structures that has the same orientation of the hydrogen bonds in each turn, and this is the orientation of hydrogen bonds. And we repeat the measurements. We injected heat here and measured the heat diffusion in that direction, and injected heat here and measured the heat diffusion in the opposite direction. And the thermalization rates are different and obey the same principle that the heat diffusion is favored for hydrogen bonds in this direction, and inverse direction is occluded. So we conclude that in the paper. So the thermal rectification obeys the asymmetrical nature of the hydrogen bond. For this part, I conclude that correlation is observed for the spatial location of allosteric pathways and heat diffusion pathways in proteins. Thermal rectification effect is observed in protein structure that is originated by the three-dimensional structure of the protein and the funnel-like structure. A minimal scale, the rectification effect arose from the asymmetrical nature of the normal length hydrogen bond with a favorite direction in that fashion. And this effect be compromised in short hydrogen bond that display as an symmetrical pattern of heat diffusion. Well, now I'm going to show you the thing that we're doing in the Center of Neuroscience. We're studying the thermosensation in living beings. In living beings, the thermal sensation are done by a family of membrane proteins called TRPs that are sensitive to heat in different range scales. And the precise mechanism for the heat activation pathways of this family remains unknown. This is a cartoon of the structure of the protein in the cell surface, which have a domain that is in the membrane, and in intracellular domain that is a huge intracellular domain. So this is the cartoon also that display the differential response of this member of the family. For instance, TRPV1 responds around 40. So when we have fever, this protein detects the heat and sends signals. TRPM8 sends cold. So when we touch cold water or cold surface, this protein is activated. Also, these proteins are activated by chili. Let's say when we eat chili, TRPV1 responds at room temperature. So also when we eat mint, despite that there is not cold, TRPMA responds, so it creates this sensation of cold. Well, here is the protein that we are studying. This TRPV1 is a very complex system. It's an ion channel that has a tetrameric structure and is an upper view. This is a lateral view. Here is the membrane, lipid membrane, and here is the intracellular domain that had been related. We believe that is responsible for heat sensing. In the upper part of the protein, let's say in this part of the protein, we have a depermeation pathway that have two constriction or gates that are closed or open to allow the ions to migrate to generate the impulses, the responses. So we have here the monomeric structure of one monomer of the protein, and we see alpha helices for that conform the pore, and a kind of a mixed structure between loops and alpha helices and beta sheets that form the intracellular domain. So the research question that we are trying to answer is how the energy is captured from the solvent and which structure are involved. Where is the thermal sensor in TRPV1? And the secondary question is how energy flow along the three-dimensional structure. This is wrong, to reach pore constriction. So for the first question, we have one hypothesis that comes from nuclear magnetic resonance that says that the most sensitive segments in a protein are the more disordered segments. So heat capacity is structure dependent, is local. And here we have a list of so-called critical temperatures. And the critical temperatures for alpha helices and beta sheet is 1000 Kelvin. So they become disorganized to higher energy. The critical temperature of loops are around 300 Kelvins. So they are soft. These structures are stiff or hard, and the C-terminal or the terminal of the protein are really activated at low temperature. So if we see again the monomer, we see that the stiff part of the protein in TRPV1 is alpha helix, and the flexible part that have the loops and the termini is more flexible. So this part, it may be the sensor. We think it's the sensor, so it can get excited by thermal energy. So that is the process that we're managing. So the heat is transferred from the solvent water to this part and not to the upper part. This is the working hypothesis, the same that I have said, that due to the increased flexibility of loops, there is an enhanced thermal susceptibility and enhanced heat capacity. So this increased thermal susceptibility facilitates the capture of the energy from the solvent. Now the second question is how the energy flow along the three-dimensional structure to reach pore constriction. For this, I am taking another evidence, it's not new, but it's recent, that says that when one injects energy in a protein, it's tend to focus in the stiffest part of it. And interestingly, catalytic site are the stiffest part of proteins. So that is a good news. Is what is intuitively expected when we increase the temperature of a media, the enzymatic activity increases and the response occurs in the catalytic site. So in this context, protein harvests heat, and this heat is transferred throughout the structure to the catalytic site. So it's good news for us. So this is the cartoon. When the energy is captured here, it may flow, vibrationally flow toward the stiffest part and to the pore constrictions. Also, we have made this ATV analysis for a monomer of TRPV1, and that reveals some, reveal the allosteric, the heat diffusion pathways. We did start with heating the red part, which is self-coupled to itself, is coupled to itself, which is around here, but generate also signals in MPD, which is the yellow part. And when we heat up MPD, it generates signals when we heat up in CTD, which is the blue part here, and a detail of the heating of CTD, transfer energy to S5. CTD, when we pump in CTD, we get signals in S5. And finally, when the heat is incorporated to S5, transfer energy to S6, where the pore constriction are located. S5 to S6, this is off diagonal element here. So there exists heat diffusion that may be pathway that may be mediating the thermalization of the protein. Yes?
The difference with the other picture you showed, because here you have a sort of fish bones.
Yes.
Yeah.
Yes.
In the other one, it was yeah, here. In the picture you showed for the other case,
yeah,
it was more concentrated over a line.
Yes, in the diagonal, because it's the scale.
Diagonal.
Because in the other the protein was very small. It was this size of the protein. So the scale is different. Now if we have more bigger protein, the scale show a thinner structure. So our working hypothesis is that the second working hypothesis that the captured heat, it may be transferred by bidirectional coupling to the stiffest side of TRPV1, the pore constriction. And the overall conclusion of the research is that the allosteric communication seems to be originated by vibrational coupling of the network of the protein contacts that naturally occurs when the protein are folded. The structural organization of the protein segment have a differential heat capacity, allowing them to harvest heat as function of their local degree of organization. The absorbed energy seems to, this is wrong, to be focalized to the stiffest part of the protein and adjacent active sites or catalytic site, such as the pore constrictions in TRPV1. And thermal rectification may play a central role in this energy focus. So this is my presentation. I should acknowledge to Fondesit, postdoctoral, regular to a Millennium Project of the CNV and Anillo Proyectos Anillos. And also thanks to Sergio Davis, Diego González, and Humberto Loguercio from physics. Daniel Aguayo from CEBIT in the University of Andes Peyu, and also to the organizing committee of SAM Julia, to Pamela, and Jose. Thank you.
Okay, questions, comments, remarks? No comments?
I have questions, a long list of questions.
Yeah. Okay.
Because, well, have you say a description of the dynamics, because you put the heat there? Have you a description of the dynamics of this phenomenon there? Because there is transmission of heat. So, because I am thinking about the problem of start producing some dynamical elementary models, let's say. You were mentioning the vibrational effect. So if we think at a microscopic point of view, there should be there, say, harmonic oscillators. So have you tried, or there is?
There are very interesting models based on the it's an entropic vision of the vibration of the dihedral angles of the backbone of the proteins, and some very interesting results are available later. I can show you later that are more analytically. You can have a set of equations. These studies are done based in molecular dynamics simulations. Everything is molecular dynamics simulation here, but they have very clever way to extract information and also to study the correlation between one segment of the protein by correlated movement with the other side based in this population analysis of the dihedral angles. It is possible, and this is the next step, because this is more, let's say, more operational. I hit and I measure, but now I want to go more professionally and to study equation of motion and energy and entropic distribution in the vibrational distribution of energy in the protein. I am very interested, so we can take a look of it. I can give you papers have been recently published. There are models.
Do you think that in this atom communication that you spoke about, the quantum effect may play some role, or the order of magnitudes of present experimental data do not allow any conclusion on this?
I think that this is phenomena that can be studied classically, but there is some evidence that have shown when a sample is irradiated with ER frequencies in the terahertz range, this similar kind of phenomenology of binding can be affected. So I think that there should be some kind of quantum description of excited states that can be perturbed by electromagnetic radiation, and that is another step that I want to take, the analysis, or let's say how, if we can electromagnetically perturb these allosteric pathways. Let's say we irradiate with a tuned laser or terahertz antenna, and if there is, can we trigger these responses by electromagnetic radiation, by electron phone coupling. So I think that quantum mechanics have a lot to say here.
These experiments have been done.
I can show you the paper. It's very recent. I get very excited when I saw it last week.
Very interesting.
Yes, it's very
Thank you.
interesting.
Okay, more questions or comments? Okay, let's thank again the speaker.